How you doing? I'm Mr. Rose, and today we're going to talk a little bit about energy, conservation of energy. More specifically, we're going to talk about some rotational kinetic energy and some translational kinetic energy at the same time. This is a very classic problem, and it's a real-world problem. Often we say, oh, let's pretend our pulley doesn't have any mass. Well, today we're going to talk about a real pulley. So I'm going to duck for a second so you can read that problem. But now that you've read the problem, I'll give you the quick overview. Hopefully you paused, read the problem. As always, I suggest trying this before you watch me solve it out. But I have a mass that I've said is 2.4 meters. It's starting 15 meters off the ground. It's going to fall down to the ground. I want to know how fast it's going when it hits the ground, considering that it's attached to this disc. This disc is a solid disc that I called mass big M. I did, for some reason, say little m was bigger than big M, but I said mass big M, 0.5 kilograms. So this has got a mass of 0.5 kilograms, this has got a mass of 2.4 kilograms, and it's going to fall 15 meters again to the ground, starting from rest. So I went right to my conservation of energy, because that seems to make sense. I know the energy of my system to start has to be the energy of my system, the energy of the system at the end. So all of the energy I have to start is just going to be the potential energy of this block with respect to the ground, because everything is at rest. So that's simple, that's just mgh, which is going to be the mass times gravity times how high it is. Very, very simple. Now, traditionally, if I ignored this as that falls down, I would have my total energy after. My total energy after would just be the kinetic energy the moment before it hits the ground. Potential energy goes away, and we never consider this disk moving or rotating. Now I have to do that. So I have my translational kinetic energy, 1/2 mv squared of this guy falling down, as well as the energy of this disk rotating, which is 1/2 I. Remember, I is our moment of inertia. 1/2 I omega squared. So the I, if you recall, this is a solid disk. I can look that up in my table of information. That solid disk has a moment of inertia, I, 1/2 mr squared. Plug that straight in. So now my conservation of energy, potential energy when this sucker hits the ground is 0, because that potential energy goes away. I'm off the screen. There we go. That goes to 0. I'm just left with my 1/2 mv squared and 1/2 I omega squared, where again, that I is how hard it is to turn that disk. Straight substitution, mgh, 1/2 mv squared, that's again the mass of my falling body, plus 1/2 times 1/2 mr squared, I looked that up in my table of information, times omega squared, that angular velocity. Now, I underlined r squared and omega squared here. Hopefully you recognize why, because if you recall, velocity, that's translational velocity, is equal to r times omega, which means r squared times omega squared is just v squared. So now I'm cooking here. Now I'm starting to see that I have mgh equals 1/2 mv squared plus 1/4, 1/2 times 1/2, 1/4, m, that's my disk, times v squared, that translational velocity. Well, if I come back over here, you can see velocity, velocity. I pulled my velocity term out. mgh is equal to v squared, 1/2 m plus 1/4 m. That is the mass of my falling body. That is the mass of my rotating disk. Bring that to the other side. The velocity of this thing hitting the ground, right? Think about it this way, and that, sorry for the pause. If you think about it this way, is if I go back to this picture, if I put something right there, I don't know, a little bug or a fly, and I have another guy, somebody right there, those two bodies will be falling at the same speed the moment he hits the ground, right? Which is why I can pull this velocity out, and now I'm talking about essentially something that is at that radius. All of that translational velocity has to be the same speed as everything else that's falling translationally. That's why this works. That's why we're allowed to do that. So again, I brought that whole thing over. My final velocity of really anything, but talk about that mass specifically, but anything attached to that mass the moment it hits the ground, is the square root of mgh, where m is my little mass, 1/2 m is the little mass, the falling body, big M is the mass of my rotating wheel, all under the square root. I may have said that already. If you compute that with my numbers, you should get a velocity of 16.32 meters per second. Well, this is one of the first examples we did that is an actual real-life example where I need to consider everything going on in my problem. You can do this differently if you want to try and use Newton's laws and force and free body diagrams. Much more difficult, but have at it if you'd like. That's all I have for you right now. Please feel free to like, comment, or subscribe to my YouTube channel. And that's all I have. You'll see me next time.